How are you doing this evening?
All right, how are you?
Pretty good.
Good deal. Have any questions before we get started? We got about 7 minutes, so plenty of time.
Don't think I have any right now.
That's cool. I haven't looked at my syllabus recently, but I know we should be having a practice test and a uh second online test, which would be the third test total. I know that's supposed to be coming up sometime soon. Might go ahead
All
and
right,
open them now.
thanks for the heads up.
Yeah. Yeah, I need to pay closer attention to the syllabus so that don't happen, but here we are. Hmm. This cold would go away. That would be awesome.
Oh yeah, my brother had one recently and it had him put down for a few days.
Yeah, it's my wife had something and it lasted like 4 or 5 weeks, and that's what I'm in now, I think. So it kind of stinks.
Oh, well, I hope you'll feel better soon.
Yeah, me too. It doesn't feel too horrible now, so I shouldn't complain that much, but still, just like how long do I have to be sick? All right, I did make practice tests. I've now called it test three, so even though it would normally be test two, but it's the third test total, so I called it practice test three. That's available, and I'm making the it disappear on the 18th, which is the day that the actual face-to-face, or excuse me, the actual online test will be due. So I hope that helps.
Gotcha.
Yay.
Thanks.
Uh, that's open. That's good. Gosh. iPad just slipped over and laid on my space bar, and couldn't figure it out. My space bar was moving all over the place. Okay, go. That worked out. I'm surprised more people haven't showed up, but I do have Infinity here, so Infinity and Jacob. Right, got 3 people now. Yay. Got another one. All right. Got another. All right. Looks like it's actual time now, so I should probably get started. Uh, thank you for the roll call. Yes, please, everyone, go ahead and text your first and last name to me. I usually call for it towards the end, just to make sure nobody just comes in and then leaves. But I think you guys know that that doesn't work out so well for you. So I'll just say I'll take the loss on the missed absent student. So like I said, we've got 8 people in here now that are students, and I wanted to ask: does anybody have any questions? We've now officially finished chapter 3 and started into chapter 4. I am not making chapter 4 due this Sunday, though. I'm leaning toward just making it the following Sunday, which will give you more than enough time. In principle, you should be able to finish it by Wednesday or Thursday of next week. Actually, there's very little uh, that you can't do probably by Monday, where I'll cover the remaining parts of the chapter 4 that I won't be able to cover today. So I'm going to go ahead and start building on the stuff that we need, uh, are building on the stuff that we have to make the stuff that we need today. So we're going to, I will address an inclined plane. I will figure out how to find certain quantities, like weight, for instance, stuff like that. Uh, and I'll make sense of why Galileo discovered that all objects fall at the same rate. So, no questions. Looks like everybody is probably uh, chatted your first and last name to me, so that's good. If you haven't, go ahead and do it, and I'll try to remember to announce that again as the night goes on. What we're doing is chapter 4, and chapter 4 is called Dynamics, Newton's Laws of Motion. Last time we talked about the 3 laws. I've got all those covered for you. I covered the first law, which basically says, in the shortest version, is an object with no net external force acting on it will have a constant velocity. That's Newton's law, or first law of motion. That's also Galileo's law of inertia. You could say it more robustly or more, with more words, sort of the opposite of succinctly. So you could say it by saying that an object in motion tends to stay in that state of motion unless acted upon by a net external force, and an object at rest tends to stay at rest unless acted upon by a net external force. But when I use the phrase that motion, an object in motion tends to stay in that state of motion, what I'm saying is the velocity, a vector quantity that has magnitude and direction, will not change. So it's not going to speed up, it's not going to slow down, and it's not going to change directions. That's as long as there's no net external force acting on the system. Because we know about vectors, I can shorten that just by using the word vector, and that's what you saw in the first case. Newton's second law says that if the net external force on this object is not zero, then the acceleration that object will get will be directly proportional to the total force acting on it, the net external force acting on it. It'll be parallel to the net external force acting on it, and it'll be inversely proportional to the mass of the object. That's Newton's third law. And then for every action, there's equal but opposite reaction is another way of saying Newton's third law. I usually say the force on object A as a result of object B, and I would call that F vector symbol with an A and then a B subscript, is equal to the negative of force sub BA. In other words, the force on B due to A, again with a vector symbol. So by reversing those subscripts, you're saying in the first case, AB means the force on A due to B, and then the second case is the force on B due to A. That's the way a Newton's third law of motion pair is supposed to work. So you need to keep that in mind. That'll help you a little bit guiding through the sections in chapter 4. So the first thing I wanted to say to you is that obviously Newton's first law mentions a force, Newton's second law mentions a force, Newton's third law mentions a force. So you might be wondering what's a force, and this is a somewhat circular definition, but the main thing is anything that you can apply to an object or a system that results in the object or the system accelerating, i.e., changing velocity, can be construed a force. Okay, so that's what forces are. Forces are the things that make objects speed up, slow down, or change direction. Okay, so that's what a force is. And in fact, what we learned last time was the force is measured in units of newtons, Newtons. And I have some more information for you. For instance, your book is telling me in one of the tables, it basically says that 1 pound, which is a measure of force in the British system of units, which, as I said, only the United States and I think the other countries, Liberia, there's literally only 2 countries that use the British system, and one of them's not Britain. Okay. In that system, the unit of force is the pound. And therefore, there's an actual conversion factor between the pound and the Newton, which is also a unit of force. There's also one between the pound and the dyne, which is another unit of force. And the conversion factor I'm talking about is 1 pound is equal to 4.45 newtons. So if you tried to solve that for 1 Newton, you'd see that 1 Newton is in fact a little less than a quarter pound. I think I introduced that backwards in the last session, so I apologize for that. I was remembering something that that I had read in a book, but I think I might have got that mixed up, and that's what happened. But the fact that your book is telling me 1 pound is equal to 4.45 newtons tells me that 1 Newton should be equal to 1 divided by 4.45 pounds. So if you divide 1 by 4.45, you'll see that number's quite a bit less than 0.25. So yes, a Newton is a little bit smaller than a quarter pound. And the other thing I think it gave us was the idea that a slug, which is the British system's unit of mass, I think it's 14.6 kilograms. So one slug's about 14.6 kilograms. The kilogram, of course, being the unit that we use in the SI system, and the slug, what we use in the British system. I will also tell you that, dang, I can't stop yawning. I am so sorry. I also want to tell you that the unit of mass, or our mass in general, is not something that changes. It's a measure. I hate this definition, but a lot of people will say it's a measure of matter that you have, which I don't think makes much sense unless I break that down and start thinking about individual atoms and how much they weigh and stuff like that. So what I like to do is say, though it didn't have to be this way, the mass that we use in Newton's law of gravity and the mass that we use in F equals ma didn't have to be the same, but they turned out to be. And the mass that we use in F equals ma on the right-hand side multiplied by a, for instance, is the equivalent of the inertia. So it's an object's reluctance to accelerate. You can tell that because when I showed you Newton's second law, we had acceleration is equal to the net force divided by the mass. And the fact that the mass is on the bottom as a denominator and the force is on the other side of the equation as a numerator, that tells you that they are thumbs up, thumbs down. So the mass means the larger it is, the harder it is to accelerate. So that sort of fits our definition of inertia. So hopefully that helps you. With that in mind, no matter where you go, you're going to have the same inertia, even down to if you're in free fall, which is what happens when you're orbiting around the Earth, or you're orbiting around the sun, or you're orbiting around the moon. Orbit experiences weightlessness. In other words, astronauts in the International Space Station, astronauts in the shuttle when we used to have that, astronauts in the various Russian spacecraft that we use to get them there now. All of those guys, when you see them experiencing weightlessness, that's because they're in free fall. It's not because there's no gravity out there. That's a common misconception. But it should be obvious to you if you take a little bit of time and think about it. What you'll realize is that the satellites that the space shuttle often used to put in orbit around the Earth, the International Space Station, which is in orbit around the Earth, the other space station thing that Russia put up some time ago is orbiting the Earth. All of those things orbit the Earth closer to the Earth than is the moon. So the idea that they're weightless out there because there's no gravity is just crazy, because we know that the moon is held to the Earth via gravity. So clearly gravity's there. So really, when you ride over a railroad track hump in your car and you get that sort of butterfly feeling in your stomach, or if you ride the Apollo's chariot at Busch Gardens and get that butterfly in your stomach, that is you experiencing essentially weightlessness. And that's because you're essentially in free fall. So that's exactly the reason that the astronauts experience weightlessness when they're orbiting the Earth or orbiting anything else for that matter. Okay. Now, in order for them to actually get weightless, they would have to go essentially infinitely far away from all masses, because the law of gravity doesn't get to zero until the distance between the two masses goes to infinity. But you can tell they fall off pretty quickly. So if you really got far away from our solar system and from other stars and planets, let's say on the order of several astronomical units, you would basically not feel any gravitational exertion towards them, and therefore you would really experience what we mean by weightlessness. Now, I've mentioned to you that the mass doesn't change from place to place to place. So, for instance, whatever force it takes me to reach such and such acceleration, that's directly related to my mass. And that's going to be the same whether I'm experiencing weightlessness in outer space. It's going to be the same if I'm on the moon. It's going to be the same if I'm on Mars. It's going to be the same if I'm on Earth. However, weight, which is really just another word for the gravitational attraction that your planet has for you, that will change from place to place. So on the moon, for instance, the gravitational acceleration is about 1/6 that of the Earth. So our weight turns out to be about 1/6 of our weight on Earth. If we went to Jupiter, the acceleration due to gravity is almost 3 times as big as the 9.8 we use on Earth. So our weight on Jupiter would be, in fact, about 3 times larger. And if you were actually out in the middle of space, really far away from any planets or asteroids, or, well, asteroids might not be that big a deal because asteroids and comets are usually kind of small compared to planets. But the main thing is, if you're really far away from all the masses, on the order of astronomical units away, then the gravitational force of attraction on you would be very, very minimal, if even measurable, and therefore you would experience weightlessness because there really was no weight there. So weight definitely changes from place to place to place, but mass doesn't. So now that we've got all that stuff done, what I want to do is turn to free fall and make some sense of what is an object's, what are the forces acting on an object. So consider an object of mass m. I'm going to share my iPad screen with you guys. Hopefully it does it trivially. Yes, it seems to be. Oh, that's not it. There we go. Okay, it should be loading up pretty soon. And what I've written down is consider an object of mass lowercase m in free fall. I decided to hyphenate free fall. I don't know why. But anyways, that's what I did. What is the names we give the force that causes free fall? Can anybody think of the name or a name of the force or forces that actually causes an object to fall at the 9.8 meters per second that Galileo showed us?
Gravity.
Gravity, yes, gravity is the phenomena that actually causes it. What do we call it on Earth, though? It's something that's a property of me, for instance, is my blank. Anybody? Give you a hint.
Wait.
Wait, there you go. Yeah, it starts with a W. So, yeah, gravitational attraction is one thing that you can use for the name of the force that causes us to go into free fall. And that's part of what I was shooting for, but it really is just part because really what I wanted was weight. That's what we're going to use day in and day out. And the other part of the question is how do you calculate it? So what I'm going to do is I am going to draw an object in free fall. So there's a little ball in free fall, right? Now that ball, since it's in free fall, that means the only force acting on it is the gravitational attraction that the Earth has for it. And that's what we call the W word, the weight. So what I'm going to do is I'm going to say acting on this body is a force W, which we call weight. Okay. Now that has to be the only force acting on it because, like I said, it's free fall. If we had air resistance, that wouldn't be free fall. If we had other forces like wind or stuff like that, that wouldn't be free fall either. So what we have here is the free body diagram that exists for a body in free fall. Now I'm going to take this and extend this line this way and call this the positive y-axis. I didn't have to. I could have made up the positive y-axis. I could have made right the positive y-axis. I could have made up and to the right at 32.7 degrees the positive y-axis. Doesn't really matter. But the main thing is what I've chosen now sets certain things to be certain values. So what we know is Newton's second law says the summation of the forces, that's all the external forces acting on the object of mass m, is equal to the object of mass m's mass times the object's acceleration a. And I put the vector symbol on top of those because this is actually a vector equation. Now, in lieu of actually dealing with vectors, you can break the individual vectors down into components, and then you get the summation of the forces in the x direction is equal to mass times acceleration in the x direction. The summation of forces in the y direction is equal to mass times acceleration in the y direction. And the summation of the forces in the z direction is equal to mass times acceleration of the z direction. Now, this is where it gets a little dicey because, for instance, vectors only have positive magnitudes, right? So there's never going to be a negative magnitude of a vector. But components of a vector are indicate their direction by using a sign. So what often happens is I'll write like the summation of forces in the y direction equals mass times acceleration in the y direction, and it'll look like I'm adding and subtracting things. That's because really the left-hand side says sigma, which means add all these things, but some of them are negative, so I just skip the time required to write a plus symbol followed by a minus sign. Okay, so just keep that in mind. Now that we have this and we're looking at the free body diagram, we can say the summation of the forces in the y direction is equal to mass times acceleration in the y direction gives us, notice there's exactly one force acting on it. That force is W, and it happens to be acting in the positive y direction. So I just put positive W. Now that's the only force. So this side represents the summation of the forces in the y direction. On the right-hand side, we have m times acceleration. Does anybody recall the symbol we use for the acceleration an object gets when it's in free fall? Asking for the symbol we use, not the number. Anybody know the number that the object accelerates at when we're in free fall?
Infinity says negative g.
Exactly. So, oh yeah, thanks. Thanks for catching that, Hannah. I got to turn that. Yes. And in fact, since I made my coordinate system such that the positive y-axis points down, it's just going to be positive g. But g was what I was looking for, so you nailed that part. Anybody have any questions? Now, I did, by the way, in case anybody just came in, it looks like people were already seeing it, but I did ask everyone to chat me your first and last name for roll. So make sure you do that if you haven't already. I know Diego came in late after I'd done that, so he might not have done it. All right, so we know that the acceleration A is in fact equal to g, and since the y-axis is positive pointing down, the acceleration will actually be a positive g. So we've got that. This side right here is the m times the a sub y. Now, what we've managed to do is we figured out the actual formula for the weight. So what we can now say is W, which is defined to be the weight of an object, is equal to the object's mass times gravitational acceleration. Now, the key thing is to realize that this G depends on where M is. So for instance, if I'm actually, let's say, hovering in a spacesuit above the thick atmosphere of Jupiter, then the G is about 29 meters per second per second. If I'm on the surface of the moon, then G is about 9.8 divided by 6, which is about 1.63. If I'm on the surface of the Earth at sea level, then G is 9.8 meters per second every second. If I go lower than sea level, it can get a little larger. And if I go higher than sea level, it can go a little smaller. In fact, I would suggest you guys, when we get to it later in the chapter on gravity, I'm going to actually have you calculate what gravitational acceleration is at the top of Mount Everest. And anybody know what the significance of Mount Everest is for the Earth? Hannah, you're muted on this one. I saw you talking, but it looks like you're muted.
I was talking to myself, but isn't it
Oh,
something like because it's like so far up, something to do with like the sea level?
yeah, it is the highest altitude on the Earth. So yeah, it's the highest point on Earth is the top of Mount Everest. So yeah, you were getting to it. So that's the farthest you can get away from the center of the Earth without leaving the Earth. So if you calculate G there, you're actually going to get G being a little bit smaller than 9.8. And then later, I'll ask you also to calculate G at the bottom of the Marianas Trench. Hopefully, you guys know that the Marianas Trench, as far as we can tell, is the deepest place. In other words, it's the place on the earth where you can still be, quote unquote, on the earth and be at the absolute closest you can to the center of the earth. Okay. Because of that being so much closer, G is a little bit bigger than 9.8 there. But again, I'll get you to do that as a calculation later in a subsequent part of the book. So everybody gets now what the formula for weight is, and hopefully you now see why I did that. I just wanted to do that to work out what the formula for weight is. Last time we actually did a problem where a bear had a weight of 1,600 newtons. Does anybody recall what its mass was last time?
It's 160 kilograms.
Yeah, it's 160. That's because 9.8 is really close to 10. So it's pretty easy to just say, hey, if the weight's 1600, then the mass must be about 160. Okay. It's obviously a little bigger than 160 because dividing about 9.8 is dividing by a smaller number than 10, but that gets you there. Okay. Now I want to see, why do all things fall at the same rate? So why do all objects fall at the same rate on Earth? Now, it actually turns out to be that way for all planets, but the one we know about right now is Earth, so that's why I said it that way. And of course, that rate is A is equal to G. Okay, so what I want you to understand is that A, from Newton's second law, that A is equal to the total force divided by the mass. Okay. Now, if the object's in free fall, if we talk about the object being in free fall, what is the summation of the forces? What force is acting, for instance, on the object that I just drew up above in the green ball?
Gravity.
Gravity, and we use a W word for that. What's that called?
Weight.
And of course, the formula is M times G, right? So the total force is W, which equals M times G. So we see that A is directly proportional to M, right? So that's one thing we discovered. So that seems to be consistent with what Aristotle taught us, where Aristotle would have said, hey, if you have a 10-kilogram stone and a 1-kilogram stone, the 10-kilogram stone is going to fall towards the earth about 10 times faster than the 1-kilogram stone. So this seems to be supporting that. Does everybody see how I'm saying that this supports A is proportional to M? Now, here's the other part. Newton's second law also says that the acceleration is inversely proportional to the mass, doesn't it? You see the M on the left-hand side of the page? We've got A vector is equal to summation of forces vector over M. That's the definition of inversely related. If on one side of the equal is a variable and on the other side of the equal is a variable, but it's on the other side of the fraction bar, then those two variables are inversely related. If they're on opposite sides of the equal, but the same side of the fraction bar, like A and summation of forces, then they're directly related. So what we found is this neat little mathematical symbol is helpful. Therefore, A is directly proportional to M over M, which means A is independent of M. Okay. Or another way of looking at it is A would be mg over M. And when you write it that way, you can see the M's cancel out and you get equals G. Okay. So now do y'all see why all objects fall at the same rate? So it seems, right, the force of attraction between the Earth and the object is directly proportional to the object's mass. So that seems like Aristotle said, but the inertia is directly proportional to the mass. In fact, it is the mass, and the inertia is inversely related to the acceleration. So yes, as the mass goes up, so too does the inertia. So the force goes up by the exact same amount that the inertia goes up. Therefore, the net effect is nothing. All right. So hopefully that helps you guys see a little bit about why Galileo was able to see that the all objects in free fall fell at the same rate. Now, what I want to do next is let's consider conceptual example 4.1. So it says a school bus comes to a sudden stop and all of the backpacks on the floor start to slide forward. What force causes them to do that? Anybody have any idea about that? So you're riding in a school bus, it's going, something like 37 miles per hour, woohoo, right? And you got book bags laying all on the floor. And then all of a sudden, someone runs out in front of the school bus. So the school bus driver hits the brakes, and then all the book bags start sliding forward. So, what force caused those book bags to start sliding? Can anybody think of a force, or is that not even the right way to say it?
Is it the acceleration?
It is related to the acceleration because what's happened when you hit the brakes in the bus is the bus is now accelerating. So if the bus was just moving at constant speed in a constant direction, the book bags wouldn't slide at all. They just stay where they were. But what matters in terms of when the bus starts to hit the brake, what's going to prevent the book bags from sliding, if anything? Can anybody think of a type of force that might help it?
Friction.
Yeah, there you go, friction. So it's really not correct to think about the book bags sliding because there's a force acting on them. It's more, and actually, if you think that way, that's why Aristotle and the science that he created worked for so long because we are Aristotelian thinkers in some sense. But the big deal is here that there's no force required to make the book bags slide towards the front. What's really happening is the book bags are riding in a moving reference frame, and that's moving with a constant velocity. And according to Newton's first law, those book bags plan on going that same velocity in that same direction for all time. So if the school bus was going 35 miles per hour, 5 degrees east of north, then the book bags are content going 35 miles per hour, 5 degrees east of north. When you start hitting the brakes, if there's not enough friction to keep them from sliding, then what's going to happen is the book bags are going to continue to try to go 35 miles per hour at a direction 5 degrees east of north, and that's why they slide. Does that help? Does everybody have an understanding of that? Hopefully. Anybody have any questions on that? So the book bag slide because not enough friction to keep them going at the new velocity of the bus. Their inertia causes them to go 35 miles per hour at 5 degrees east of north. Okay, so that's just the example I gave you. Hopefully that'll bring up enough memory when you see the notes or if you take your own notes to make some sense of it. Any questions on that one? All right, after that, your book talks about something called inertial reference frames. That's kind of a big deal, so I want to make sure I cover that. One thing I want to tell you is that Newton's laws of motion can be made to work in non-inertial reference frames, but in general, they're not. So if you ever choose a coordinate system tied to something that's accelerating, then F equals ma is not necessarily going to work. Okay. So what is an inertial frame? Well, an inertial frame is a frame in which Galileo's law of inertia seems to be holding, right? So remember, Galileo's law of inertia is basically the same thing as Newton's first law of motion, which says an object in motion tends to stay in that state of motion unless acted upon by a net external force. So if you just see something, you're looking through a video camera at what you think might be an inertial reference frame, and you look through the camera at the area, and all of a sudden you see a ball just sitting there with no velocity and nothing touching it, and all of a sudden it starts to accelerate outside of the screen and disappears, then you'd say, well, that appeared to me as if a ball just violated Galileo's law of inertia. And if that happened, that would be evidence that the frame of reference that you were looking at, the one in which the ball all of a sudden started speeding up without nothing touching it, that frame of reference is not an inertial reference frame. So basically any reference frame that is, or any coordinate system, you might say, that's actually accelerating is not going to be an inertial reference frame. A neat example is, and this actually comes up, we're going to ideally in 241, we'll also cover a little bit of special relativity. And special relativity has two postulates. The first postulate is the laws of physics are the same for all inertial observers. And what Newton or what Einstein did there was he tried to take out gravity so that he could treat the laws of nature the way he wanted to without dealing with gravity, because he knew that was too big of a problem right then. He was the only one that knew there was a problem with physics, specifically because he had looked at the paradoxes that came from Maxwell's equations. So he tried to simplify the universe by only considering inertial reference frames. And the reason why that cuts out gravity is if you consider watching a video of our solar system, what you'd see is the sun sort of sitting still. Obviously, if you set up the camera so that the sun's sitting still in it, then yeah, the sun's going to continue to look like it's sitting still. You might notice some wobbling back and forth. But the main thing is you would see the Earth going not in a straight line, but going in a very near circle. It's actually an ellipse. And the only way that's possible, according to Newton's law, first law of motion, or Galileo's law of inertia, is that there must be a net external force acting on Earth. But because you don't see anything touching Earth, then Newton would have you call that a non-inertial reference frame, because to us it appears that for no good reason the Earth is accelerating. Okay. In other words, Einstein's saying, hey, I'm not willing to accept what Newton called gravity, which can reach out over space and pull on something without touching it. I think that's a problem, just like Newton thought it was a problem when he introduced it. And I'm going to treat it like it's just a weird quirk of a reference system. And then ultimately, his interpretation turned out to be right. So we accept it. So just keep that in mind. And inertial reference frames are what you need to make Newton's laws of motion work properly. You can make them work properly anyways, but it takes a lot of work. Okay. Even the Earth's rotation makes it a non-inertial reference frame, but in almost all practical instances, you can treat it as it's inertial and it's not going to harm anything. Okay. So now we go on to mass, and that's like I told you before. I'm going to make a little mini table, if you will. So let's say there's something that is measured and it's called a force. We're going to have an example of it. And then we're going to have the British system. And then we're going to have the SI system, which is what we use. And then we're going to have another quantity called mass. Okay. So an example of a force would be weight. Whoa. Okay. And the British unit of weight is the pound. Okay. The SI unit of weight is the Newton. And this is where I'll tell you that 1 pound is equal to 4.45 newtons. So there's your conversion factor. Now mass, you could say an example of that would be your mass M. The British unit for that is the slug, which you can probably immediately see why we don't use the unit of mass in the British system. I don't think my wife would like me referring to her as weighing, 5 slugs, right? So now the unit in the SI system is in fact the kilogram. So that hopefully gives you a little bit of insight into mass versus accelerate or versus force versus weight. Hopefully that also lets you realize, I'm going to write this down now. 1 slug is equal to 14.6 kilograms. But like I said, we already found out that mass is something that doesn't change from place to place to place. The only way you change your mass is by dieting or gaining weight or something like that. It's not going to change from moving from one location to the other. Whereas the weight actually does change. So that's a big difference. Another big difference is the units. And then there's another system called CGS, which I can put over here. And in this case, the unit of force is called the dyne, which if you've ever heard of a dynamometer, anybody ever heard of a dynamometer? Okay, so that's a neat word. People that are really into cars sometimes have heard of dynamometers because that's what you use to determine the horsepower, the torque, the thrust, or whatever of an engine. That's a dyne, and in the mass, it's actually a gram in the CGS system. And we have another interesting fact, specifically 1 dyne is equal to 10 to the negative 5th newtons. You might be able to make sense of that because if you look at the CGS system, which is centimeters, grams, seconds, can anybody guess what G would be in centimeters per second instead of meters per second? So what do you think 9.80 is going to become when I change that unit to centimeters per second? Y'all see that it'll be 980? So 980 centimeters per second per second. Now, what about in going from kilograms to grams? Do you see that the weight is going to go up by a factor of 1,000? So notice the G went from 9.8 to 980, so that's up a factor of 100. The kilogram going to the gram means that number is going to go from like 1 kilogram to 1,000 grams. If you take 100 and multiply it by 1,000, you get 100,000, which is 10 to the fifth. And now you see why one dyne is 10 to the negative fifth newtons. And that's supposed to be a capital N. I don't know why I wrote it as a lowercase n. That's not right. Okay, so hopefully that dispels the mystery of why the dyne is off by 10 to the negative fifth from the Newton. Any questions on that? Okay, so let's look at a problem. What force is required to accelerate a 1,500 kilogram car at 1/2 G? And then part B, how about a 250 gram cantaloupe? Oh crap, I can't spell cantaloupe. I think I did. We'll call it a day on that one. Okay, so that's going to be our problem. Our problems, plural, I guess. So for part A, we're trying to find what the force is. We want to know F is equal to question mark when M is equal to 1,500 kilograms and A is equal to 1/2 G, which equals 4.90 meters per second per second. And of course, we know the summation of the forces is equal to mass times acceleration. We can make this one-dimensional. So in going 1D, what we're going to say is the net force is equal to 1,500 kilograms times 4.90 meters per second every second. Now, if I multiplied 1,000 by 1,500, or excuse me, yeah, if I multiplied 1,000 by 4.90, I'd get 4,900. And then if I multiplied half of 1,000 by it, I'd get half as much, which would be 2,450. So if I add 2,450 to 4,900, so 2,450 to 4,900, I think you can see that this ends up getting me 7,350 newtons. So that's how I did that arithmetic, just to avoid having to actually do put something in my calculator. So it takes 7,350 newtons. Let's double check that. Checking my math, 1,500 times 4.9 gives me 7,350. So that checks. Now let's try part B. part B, F is equal to question mark, but M is equal to, notice it was 250 grams, so that becomes 0.250 kilograms, because if we're using equations in this book, unless we make up one specifically for some particular experiment where the mass is in grams or something, we always have to use kilograms. And A again is 4.90 meters per second every second. Then what we get is the summation of the forces is equal to 0.250 kilograms times 4.90 meters per second every second. Now, 0.250 is 1/4. So I know 1/4 of 4 is 1. And then I know half of 0.9 is 0.45. And then I know half of 0.45 is 0.225. So I'm going to say this example gives me a result of 225 newtons, 1.225 newtons. Any questions on that? So I'm just trying to avoid using my calculator. That's also good for your brain, by the way. Staves off Alzheimer's and all that good stuff. So that's some pretty straightforward, simple stuff. Let's try this. I'm going to do another example. So this time, what is the average force required to stop a 1,500 kilogram car traveling at let's say 120 kilometers per hour and within a stopping distance of 60.0 meters. Okay. So that's a problem we want to solve. Now, what I want is a force. So we want to know F equals question mark, and I'll put a AVG down here to let us know that, hey, this might be an approximation because they literally asked us for an average force. So that's what I want to know is the force. What I do know is the mass is equal to 1,500 kilograms. And what I do know is the initial velocity is 120 kilometers per hour, which I need to make into meters per second, which means I have to divide it by 3.6. But just to make sure you're all on the same page with that, that's because 1 hour is equal to 3,600 seconds. And that's because 1 kilometer is equal to 1,000 meters. So you're basically multiplying by 1,000 and then dividing by 3,600. So clearly you're just dividing by 3.6. So 120 divided by 3.6 gives me 33.3 meters per second. That's the initial velocity. Now they said we were required to stop a vehicle. So I'm going to say V final is equal to 0. And I'm also going to say delta X, which would be X final minus x initial is going to be 60.0 meters. I also know that the summation of the forces is equal to mass times acceleration, but I don't know the acceleration. So can anybody tell me, given the symbols that we have, the values that we have, anybody tell me an equation that might help us find the acceleration? So chapter 2 equation from kinematics.
Could we
We
use velocity squared equals velocity initial squared minus 2a of x minus x initial?
Yep, that's the easiest one. I'm going to show you an alternate way too. So that's kind of neat, but yeah, that is exactly the one I was shooting for. So v squared is equal to v initial squared plus 2a x minus x0 is what we're going to use. When I plug in those numbers, the final velocity is 0, so I just get 0. The initial velocity, of course, is 33.33 meters per second. Notice putting the units in is a really good thing if you have the space and time. Now I'm going to say that's plus 2 times a times 60.0 meters. So that gives me a is equal to a negative. Notice if I pull the 2a times 60 to the left, it becomes negative. And that's why I've got that negative there. If I take the 33.33 and just square that, what I get is 1111.11. So I'm going to say this is negative 1111.11, and that's meters squared per second squared. That's going to be divided by 2 times 60.0 meters. And that gives me 9.259. Negative, of course, meters per second. So that's a pretty big ask to ask something to go from a 1,500 kilogram car to go from 120 kilometers per hour to 0 in 60 meters. That's an acceleration of 9.2. That's almost G, right? G is 9.8. So that's a good fraction of a G. Not unreasonable for a braking. I mean, it's pretty common to have braking acceleration on the order of G, but not a whole lot, and not 98% of the cars. So we have that, but that wasn't really what they asked for. Now I use the summation forces equals mass times acceleration to find the force. So I'll do that right here. That's going to be 1,500 kilograms. And I'm just dropping the negative sign because we really only care about the magnitude. The negative just means that we've obviously got to apply a force in the opposite direction the car was initially going. So if I take this and multiply it by 1,500, I get 1.39 times 10 to the 4th newtons. And that's the answer that they asked for. So I'll put this in extra bold red. Okay, any questions on that? Now, let me show you an alternate way there's literally courses at various colleges and universities where instructors refuse to let you use the v squared equals v0 squared plus 2ax. So that's one reason I'd like to show you a way without using that. Another reason is it turns out one of the equations I use here, at least for some of the practice tests, make a couple of problems really easy if you remember to use it. So that's what I'm going to do. So here's an alternate solution. Okay. What I know is V is equal to V0 plus AT, and that's for average acceleration. And of course, that gives us the average acceleration is V minus V0 over T. I know V0 and I know V. So check, check. But that one I don't know, and that one I don't know. Okay. I also know that the summation forces is equal to mass times acceleration, and the force is what I want to know. Okay. So if I can get the acceleration, I can plug it into here. I do know the mass is 1,500 kilograms, so I at least have that. I know that V is equal to 0 meters per second, and I know that V0 is equal to 33.33 meters per second. Oops. But that's pretty much all I know. Okay. So if I could figure out a way to find out time, then I could actually calculate the acceleration. Well, guess what? Here's what I'm going to use. One of the kinematic equations I know is x is equal to x0 plus v bar t. Okay. And another equation I know is v bar is equal to v plus v0 over 2, and that's for constant acceleration. Now, the equation we used last time, the v squared equals v0 squared plus 2a x minus x0, that's for constant acceleration as well. This is where we're getting the idea that the force is going to come out as like an average, because there's no guarantee the acceleration that we're dealing with really has to be a constant. So by calculating an average acceleration, we're calculating an average force. Okay. Now, this version right here of the average velocity is not something that a lot of people use. That's why I'm taking the time to show it to you, because like I said, there's certain problems in the practice tests and certain problems in the homeworks that can be made a lot easier using this. So I just want to remind you it exists. So let's first off calculate V bar. So V bar is equal to the initial velocity, which is 33.33 meters per second, plus 0, and then all that's going to be divided by 2. So I'll say 33.33 divided by 2 gives me 16.665 meters per second, and that's 2 extra sig figs. Now, if I look at this other equation, I can see that T is actually equal to x minus x0 over v bar. That will allow me to plug it in the A equation up above. So I'm going to say T is equal to x minus x0. I'm just going to say x0 is 0, and this is 60.0 meters. That's another thing we knew. Okay, so what I'm going to do is say 60.0 meters divided by 16.665 meters per second. So I'll do 60 divided by the 16.66, and that gives me 3.60, and that's 0 again, and 4. So that gives me 3.6004 seconds is the time required. So now I can finally say A bar is going to equal basically V minus V0. Well, the final velocity is 0. The initial velocity is 33.33 meters per second. And then I'm going to divide it by the time, which is 3.6004 seconds. And that's going to give me notice also we get a negative here again. So this gives me a negative oh, this is weird. Ah, that's why. So this gives me negative 9.25741 meters per second. Notice that's not too terribly far from the original acceleration we got, which was 9.259. So again, I'll just put a lighter red box around it because we really aren't looking for that. Now I'll use the summation of the forces is equal to mass times acceleration, which is 1,500 kilograms times, again, I'm going to drop the negative sign because all I care about really is the magnitude here. So I'm going to multiply that by 9.25741, which obviously has a buttload of extra sig figs. And that's meters per second per second. So ultimately, I get the summation of the forces is equal to 1.38. Actually, both of them should have been written as 1.39. Oh, I did write the other one as 1.39. Good. So 1.3888 is what it came out to be. So I'm going to say 1.39 times 10 to the fourth newtons is the actual force. So notice we got the same result. And that was a way where we didn't have to use the V squared equals V0 squared plus 2AX. Any questions on that one? All right. So your book then talks about the precise definition of mass. Definitely that's something you should read. We don't really get much that you could solve problems out of, but I would definitely recommend you reading all these chapters anyways. Let's go on to the next section, which is Newton's third law. We've already discussed that. I'll move along with that as well. Oh, this is actually a good result, a good one. Your book is asking you what exerts the force to move a car or what makes a car go forward. Anybody have an idea? So you actually are sitting in a car and you hit the accelerator. The car takes off, assuming it's in forward, takes off forward. What is actually applying the force to the car that makes the car move forward? Anybody?
Isn't it like the grooves in the tire or the asphalt?
Yeah, that second part's a better answer. So what happens when you actually hit the accelerator is you're pushing gas, obviously, into the piston. That causes more explosions to happen more frequently. That actually causes the engine to rotate more rapidly. That turns the transmission. That turns the drive shaft and the differential, and then therefore it starts to attempt to turn the rear axle or the front axle, depending on what kind of vehicle you have. Now, What then happens if your car is not so powerful that it makes the tire spin so fast that friction can't hold it? If it really is that powerful, then you'll just spin out and nothing will happen. If you have a normal car, it's not that powerful. Okay. If you have a Honda Accord, it's not that powerful. If you have a Prius, it's definitely not that powerful. But the main thing is when you actually hit that accelerator, the mechanism of the car tries to rotate their tires forward. And if there's enough friction to stop that from happening, then what literally happens is the friction from the asphalt acting on the tire holds the tire from rotating freely as the tire rotates forward, which pushes the vehicle forward. So it is actually the road or the asphalt, as Caden said, that actually applies the force to help a car move. Any questions on that one? Now, your book also does this nice thing regarding Michelangelo's obviously moron helper. Sorry, I like to act like I'm really a mean person that calls people morons and stuff like that, but I'm really not that way. I just kind of have a fun time pretending like I'm Sheldon. So, anyways, conceptual example 4.5, third law clarification. So listen to this. This is almost verbatim a question that I normally ask anyways, but in the 5th edition, your book decided to go ahead and make it a conceptual example. So Michelangelo, y'all know him, right? Famous artist. Michelangelo's assistant has been assigned the task of moving a block of marble using a sled. He says to his boss, when I exert a forward force on the sled exerts an equal and opposite force backward. So how can I ever start it moving? No matter how hard I pull, the backward reaction force always equals my forward force. So the net force must be 0. I'll never be able to move this load. Is he correct? Anybody see the problem there? I've generally never had anybody get this right, so don't feel too bad if it doesn't jump out at you. But one of the key aspects that I've been trying to focus on when I talk about Newton's third law is Newton's third law pairs. So when I say, for instance, Newton's third law is the force on object A due to object B is equal to the negative of the force on object B due to object A, I'm doing that for a very specific reason or purpose. The reason is to let you know that the two objects have to be the same. So in one case, A is getting acted on by B. In the other case, B is getting acted on by A. So when this says, he says to his boss, when I exert a forward force on the sled, so what is the assistant applying the force to? Let me read it again. He says to his boss, when I exert a forward force on the sled.
The sled.
Right. So he's applying a force to the sled. He says the sled exerts an equal and opposite force backwards. So what's the force the sled is applying? What's it applying it to? It is an equal and opposite, so it could be a Newton's third law problem. So he says the sled exerts an equal and opposite force backward. What is that sled applying a force to?
The ground?
It's actually applying it to the assistant. But the good news is what you said is still helpful, because what you realized is that the force the assistant is putting on the sled is a force on the sled. The force the sled is putting backwards is not on the sled. So those two forces should never be added, right? F equals ma means add all the forces on M. These two forces are equal and opposite, but they're acting on entirely different things. So there's no reason to ever add them together. In fact, if you want to calculate the acceleration of the sled, You only need the forces on the what? On the boy or on the sled or on the assistant or on the sled? If you want to calculate the acceleration of the sled, you only need the forces on the what?
On the sled?
Exactly. So the force that the sled applies to the person doesn't matter at all. Yeah, it's going to be equal to the force the person's applying to the sled, but so what? As long as I've got my shoes on and have enough grip, then that force is going to be handled by my friction force between my shoes and the ground, and I can still push the sled. So that's the key thing to remember is action-reaction pairs in Newton's third law should never act on the same thing because they're literally on two opposite things. That's why I said AB and then BA. All right, so that was another good problem to go over. Let's work on another one now. Neat thing here. So if you were to look at, say, my phone sitting on a desk like this, so let's pretend my hand's a desk, right? If you look at my phone, what you conclude is clearly the phone is not accelerating. So that seems to be obeying Newton's first law. An object in motion tends to stay in that state of motion unless acted upon by a net external force. Does anybody know of any force acting on my phone sitting right here on this desk that looks a lot like a hand?
Wait.
Yeah, you're applying a positive force up with your hand.
Okay, that's one thing. What about the other force?
Gravitational force.
Yeah, that's the answer I expected. You actually went ahead, so that's a good thing. You actually knew ahead of time. So what I was going to do is use Newton's first law and say, hey, this object is clearly not accelerating, so the net external force must be zero. But I know for a fact gravity's pulling on it, so I know for a fact there's a force downward. Now, the fact that the net force must be zero means that there must be at least one other force because gravity can't be zero. The gravitational force can't be zero here. So that other force is in fact the normal force, which I normally call F sub n. Okay. And just from that, we were able to conclude that an inanimate object like a table actually applies a force. So let's look at, for instance, this little example. Let's look at a box sitting on a level surface like this. Let's say the box has a mass of 10.0 kilograms. And I know for a fact that the weight acting on this thing is downwards, and that's a 98.0 Newton force acting in the downward direction. Now, we've also figured out that according to Newton's first law, there must be a second force counteracting that. So we know it has to point upward. And in this case, it's actually perpendicular to the surface. But the words perpendicular to a surface isn't the mathematically correct term. The mathematically correct term is really normal. So that's why they call it the normal force. So now what I'm going to do is I'm going to use the summation of the forces in the y direction equals mass times acceleration in the y direction. If I got a 10 kilogram box sitting on a table, do you expect it to jump up or to, accelerate downward through the surface of the table? No. So what this is telling us is that the velocity in the y direction is zero. And if you wait a little bit, it's still zero. And if you wait a little bit, it's still zero. When you have the velocity zero and then you wait and it's still zero, that's the definition of zero acceleration. So now I can just say Fn, which points in the positive direction, therefore is positive. And really, remember, we are adding these, but because the component of the weight in the y direction is in fact in the negative direction, I'm going to write minus 98.0 newtons is equal to zero. So I reach the conclusion that Fn is equal to 98.0 newtons. So that's what the normal force is for a 10 kilogram object sitting on a level table and not accelerating. You might think in general, oh, I bet the normal force is always the weight. Well, that's what I'm getting ready to show you is not necessarily the case. So let's do this. I'm going to separate this like here, here, and then here. And now let's consider a block like this. Let's say the weight is 20.0 kilograms. Let's say this is horizontal, and I put a force of 40.0 newtons at 37 degrees like that. And this is sitting on a level surface. What I want to know is what is the normal force and what is the acceleration in the x direction. So I'm going to draw a free body diagram. I'm going to start off by drawing my coordinate axes. So there's my x-axis, there's my y-axis, there's my 20.0 kilograms. I have acting on it 196.0 newtons. Notice that's 20 times 9.8. I have acting on it as well Fn, and I also have acting on it this force, which doesn't point in any direction that's helpful, but its magnitude is 40.0 newtons and its angle is 37 degrees, which hopefully y'all recognize that looks a lot like the 3-4-5 triangle. Since it looks like the 3-4-5 triangle, remember the 3-4-5 would be 3, 4, 5, and 37 would be down at this end. In order for me to make that 5 into 40, I have to multiply by 8. So what that means is the vertical or y component of the normal force is in fact equal to 3 times 8 or 24.0 newtons. And the horizontal component of the force, F, and actually that's not supposed to be F normal. Sorry about that. That's just supposed to be F. So that's just F sub Y. And this one's just F sub X. And of course, that has to be multiplied by 8 as well. So 8 times 4 is 32. So I'm going to say this one's 32.0 newtons. When I do the summation forces in the y direction equals mass times acceleration in the y direction, I again recognize that the box is not going to be bouncing up and down. So the acceleration in y direction should be 0. But notice what happens with this one. I get Fn plus 24.0 newtons minus 196.0 newtons is equal to 0. So that lets me know that Fn is actually equal to, when the 196 comes to the other side, it'll be positive, and then I subtract 24, that'll be 172. So that's what the normal force is, 172 newtons. Now, what's the acceleration? That's the summation of the forces in the x direction equals mass times acceleration in the x direction. But that's the only acceleration, so I stopped subscripting it. And we see the only force acting in the x direction is the 32.0 newtons. And that's equal to the 20.0 kilograms times A. So A is equal to 32 divided by 20. That's 16 or 1.60 meters per second per second. Does that make sense? All right, we ran a little bit out of time. It's like 6:42 now. I want to show you one more thing so you can get working on inclined planes. So just real quick, if you had an inclined plane like this at an angle, say theta, you might think, okay, well, I have a mass right here, and I would say the force due to gravity points straight down. That's W is equal to mg. And you might want to put your x-axis horizontal, your y-axis vertical, but it turns out that's not very helpful. In fact, when you're doing an inclined plane, a lot of times it's smarter to draw the axes tilted. So I'm going to call that y prime, and I'm going to call this x prime. Okay, y'all are free to go. Like I said, if you need to, it's fine. I'm going to go ahead and finish this out real quick. Now I'm going to draw my free body diagram, and my free body diagram is going to have the x-axis pointing down this way and the y-axis pointing down this way, and it's going to have mg this way. Now, the main thing you got to remember is this angle right here is theta, the angle of the incline. But if you look closely, you'll see that this is also a triangle, and it's a right triangle. So this angle right here has to be 90 minus theta. That makes sense? Then if you look, this angle right here has to be 90 degrees. So this angle right in here must be 90 degrees minus 90 degrees minus theta, which I think you can see equals theta. This is the whole part that we needed here. So what I want you to see is now you can break this weight vector. Darn it. We can break this weight vector into a component parallel to the y-axis and into a component parallel to the x-axis. So this is weight sub y, which is equal to mg cosine theta. And this is weight sub x, which equals mg sine theta. Now you can do essentially everything from this chapter. The only thing you can't do yet is the Atwood type machines with pulleys, but we're going to cover that next time, so don't worry about it. I just wanted to make sure you could break this down like that. That's something that's going to happen over and over and over and over and over again in this course. So you guys are free to go. Thank you for sticking around. I'm sorry for keeping you a little late. Go have fun. Have a nice weekend. Stay safe. And I'll wait for the last person to leave in case anybody has any questions.
Thank you.
Thank
Have
you.
a good
I'll
one.
see you Monday.
Thank you. I'll see you guys Monday too.
Just me.
Oh, yes, that's true. Thanks. Okay. Hey, Shaya, how you doing?